Hi. So the question today is, there is a no cloning theorem. Sorry. There is a no cloning theorem, and there is stimulated emission. So this no cloning theorem states that no arbitrary quantum state can be copied exactly. So an stimulated emission says that you have an atom in which, if your atom is in the excited state and a photon with certain polarization and frequency and direction comes, identical copy of that photon will be generated when there is stimulated emission. So doesn't this stimulated emission makes a way to contradict the no cloning theorem? So the first explanation, which is a little physical and might be vague, this has not been very much explained well in the literature, but one of the explanation is when you have a two-level system, for example, and if you have a photon with certain polarization, so we'll be talking in the polarization domain. So if you have a photon with certain polarization and there happens a stimulated emission, you will get an identical copy of this photon which will have the same polarization, thus violating the no cloning theorem. But in this type of atomic system, you have an equal probability of spontaneous emission. I'm sorry, that's wrong. You also have an equal probability of spontaneous emission. This is spontaneous emission, and this one is stimulated emission. So when the spontaneous emission happens, the generated photon will be in a random polarization state. So that will, so you never know the state you are getting. You initially do not know the polarization state if you have to apply this no cloning theorem in applications. So you do not know the polarization state of this photon, but you want to make an identical copy of that photon. So you put that, you insert that photon in this system and you expect identical copy, but you never know whether it went through a stimulated emission or a spontaneous emission. This was one of the explanation. Now we'll go a little bit mathematical and see a better explanation than this. All right, now, so let us suppose you have a system which can be anything. Let we define that system with a device, say D. So that D is in your initial state, and you have a polarization state, say S. When you insert this, you have a device in some certain state and your photon in this certain polarization state S. Now you want to transform this to a state which has two photons with the same polarization, and also the device may change to a different state, let's say, that corresponds to this polarization. This can be anything. I mean, the device may change or may not change, but let us suppose in general it changes to a state corresponding to the polarization S. All right. Now let us suppose you have this device in the initial state D naught, and you have a horizontal polarization. You expect it to go to state DH, and you have a two photon state with both with horizontal polarization. Now you have this D naught, the system, and let's take you insert a vertical polarization. Now you have this system in this dv state, and you have identical copy of the photon. Now we will consider this and we will consider this. Now let us suppose you have a 45-degree polarized photon. So that can be written as, let's say that the state be phi, and that can be written as 1 over root 2 a horizontal plus a vertical. Cool. Now we apply this to the same system and we now see what we get. So when this d naught is applied to this 45-degree polarized photon, what you should get is, or we can write this as equal to 1 over root 2 d naught horizontal plus d naught vertical. Cool. Now according to the equations this 1 and 2, this should be transformed to a state dh horizontal plus dv and vertical. Okay, now you must be wondering why this dh and dv are different. You may take them to be same, you can take them to be d naught. Let's suppose the system doesn't change at all. So there is another possibility where this can be changed to 1 over root 2. Let's say this d, okay, let's carry that outside. Let it be df, and then you have a horizontal plus a vertical state. All right, now we will recall something which we might have studied. So a two-photon state can be written in terms of raising operators as 1 over root 2 a dagger square over the vacuum state. Okay, now we have 45-degree polarized state. So for that, if you have say, let's write 45-degree polarized state as a plus state. So if you have a 2 plus states, then this operator, instead of this, we would be writing 1 over root 2 a horizontal, no, sorry, we would be writing a horizontal dagger plus a vertical dagger and whole square, right? So this would make a photon with certain polarization. Let's say if this is in horizontal, this operator should correspond to her horizontal, and this complete is a 45-degree operator, raising operator. Now let's see how we can do this. So the system is in your d naught state. Now we have a photon with 45-degree polarization. So can we write as it at like this, your initial state? We can also write it like this, 1 over root 2. So this one is here, and this we will be writing again. So this is 1 over root 2. Sorry, my handwriting is so bad. 1 over root 2 a horizontal dagger plus a vertical dagger and whole square, and that should be applied to a vacuum state. Now let's just square everything. So we can write is d naught equals to d naught times 1 over root 2, and what you have is square of everything. So this square is a h dagger square over 2 plus a v dagger square over 2 plus 2 times this into this, so nothing remains there. So that is a horizontal dagger plus a in times a vertical dagger, and whole is applied to this vacuum state. Now when you convert this, apply this operators to the vacuum state, what you get is d naught 1 over root 2, 1 over root 2. You have 2 horizontal photons, 1 over root 2, because this again when you apply this root 2 goes here, so root 2 time divided by 2 will be 1 by root 2. Now this plus 1 over root 2, I'm sorry again, vertical plus nothing here, and so a horizontal and a vertical state. So basically if you relate this one to either of these two, so this one is basically what you expect if your whole 45-degree state is copied. You should get something like this. But if you have a copying system, you should get either this or this, which are in no way identical. Okay, so this one is not at all the same as this. That's why you cannot have a copying system, because a copying system should do to your 45-degree polarization something like this, but actually does like this. I think the explanation is clear. And this one more very small point. So this one, if you calculate the probabilities, this one has a probability of 1 by 4. This one has probability of 1 by 4, and this one has probability of 1 by 2. So basically you will get horizontal, you get vertical, and you also get horizontal, vertical. So I think that's clear. Thank you.